Hello everyone, welcome back to another video of Math and Maths. And in this video, of course, I'm going to show you the first paper uh, on the snowball problem. And essentially, this paper is pretty much, uh, a mathematical model, I guess. You could call it, a mathematical model that is written in LaTeX form. It seems like, it was written for a particular competition, a mathematical modeling competition. Not sure which one it is, but I know it's from 2008, and it is from the University of Colombia, the National University of Colombia, and it's from a while ago. So, and this is about the comparative kinetics of the snowball with respect to other dynamical objects. So basically, the paper is not to determine particular characteristics only about the snowball rolling down the snowy hill, but it's also to compare it, to the dynamical behavior of other objects, like just the simpler versions. Like in this case, they're going to talk about a skier, going down the hill with no friction, and I think they're also going to talk about, I think it's just a regular ball with slipping or with not slipping. Okay. So here they just give a little introduction. They tell us that, of course, it's going to have a problem that has a combination of translation or rotational dynamics. It has a variable mass system, right? Because it's going to pick up more mass as it rolls down the hill. It's going to have normal and tangential forces. That's always the case when it's rolling, of course. And radius of curvature, okay, for a trajectory. So you see, in my problem, right? My problem, I didn't really consider other trajectories. I just, imagine just a straight downhill slope. Uh, I mean, of course, realistically, you'll hardly find any of those, but you could certainly make an experiment. You could make an experiment, and I do want to make an experiment once it starts snowing. Like, I want it to snow a lot so that I could, I would eventually be able to set up the experiment with a hill, hopefully long enough, full of snow, and then just like take a ball, a snowball, and just start rolling it and see if I could probably, I'll see how to essentially measure all of the little things that involve the experiment, like the speed, the time. I guess I gotta get a stopwatch, maybe some, force sensors, right? Some force sensors, and yeah, and then I guess, a balance to check for the weight before and after. Um, you know, so for this one, they are just going to talk about different trajectories of the snowball. And okay, so of course the volume is going to be growing. The environmental conditions are considered, and they're going to, basically start with assumptions. So usually when you do mathematical models, when you model something, you start off with assumptions to make the math problem simpler, right? Of course, ideally, if there were no assumptions at all, right? If it's just completely realistic, it'll be very complicated, right? And that's what I'm trying to find. This paper did well, right? I mean, I understand the paper, I get it, I get everything, but they failed in something, right? They didn't they misunderstood something when they assumed, right? So when they wrote one of the assumptions. So let's see. They're gonna call SB the snowball. S and F is gonna be the skier, okay, and then the skier sliding with friction is SF, okay, and they're gonna consider also a ball with constant mass and volume V. So today we'll just go over a few parts of this section. First section, section 2, and so for the second section, they're going to talk about the basic assumptions and write out the equations, right, of the motion. So let's see if maybe we could go over that. They're going to do some analysis, right, and compare it to the other dynamical systems with the regular, ball rolling down the hill, and then with the skier sliding with friction. Okay, so here are the assumptions that they bring about, and so So here's what they do. They say that the problem does not have any analytical solution. Okay, they say that the problem has no analytical solution. Okay, that's kind of disappointing, right? No analytical solution whatsoever. That disappoints me right there, because if there's no analytical solution, then how are we going to be able to find, right? How are we going to be able to find the functions of the row? So row in terms of, I guess, uh, to make things simpler, you should probably find row in terms of the radius, I guess, row in terms of the radius, right? Because it's going to be changing. What's going to be that function, right? What's going to be that function? Or maybe once you have row, what's going to be row as a function of the mass or the radius, or both of those, right? Since it's going to be two variables changing constantly. So what is going to be this function as well, right? And what if we include the time, right? The time as well. I mean, usually you wouldn't have to deal with time unless you bring Newton-second law, but that would be to find the acceleration, right? So, but yeah, it's kind of disappointing, no analytical solution. They say no analytical solution, so it has to be solved numerically. We have listed the numerical values assumed in this paper in table 1, in page 8. Besides, we make the following assumptions in order to get equation of motion. So the first assumption is that the snowball is always spherical. Meanwhile, it's growing in acquired mass. The density is constant as well. So, you know, if it's always the same shape, right? Well, things calculations shouldn't be that impossible, right? I mean, that's what my first guess will be. But of course, it's still a very non-trivial problem, even though if it's this is the hill, or maybe they have different paths, right? They could have different paths, and then the ball, well, it's always spherical, right? I mean, imagine a snowball rolling down the hill and always being spherical. Realistically, I don't think that's what's gonna happen, right? Because the snowball is only going to be touching only a portion of that body is going to be touching only a portion of that body on the ground, on the slope. And I think theoretically it should only be 1 point, right? Should only be 1 point, right, tangential to the snowball, the spherical snowball at first, right? Assuming that at first it's spherical, uh, it should only be touching 1 point, which means that it's going to start gathering snow, not uniformly, but ununiformly. So at first you're going to have a center of mass, uh, you know, constantly shifting, right? Getting closer and closer to where the most proportional mass, so that you have an equal proportion of mass all over. And so, at first you're gonna start. So this is the snowball, and then there's gonna be an inequality in the distribution of the snow. I'm not even sure if once this reaches such enough height that it will just slant. It will basically fall over and change paths completely, right? It will change paths completely. So that's why maybe they didn't want to do it as that, because if it's just constantly spherical all over, right, the trip, then well, we can say that rho is just it's a constant, right? Rho is going to be a constant, um, but well, not really. It's just uniform, right? So the distribution of mass is uniform, so it's not constant. It's going to be uniform, right? Since rho equals to the density is the mass over the volume. Of course, the mass is changing as well as the volume. So given that, if the volume increases, right, mass increases, well, uh, everything is essentially is going to stay the same. Right? It's going to stay the same because it's the uniform shape all over. So that's the assumption. I guess it's a pretty understandable assumption. And then the second assumption is it is supposed that there is only 1 point of contact. Okay, only 1 point of contact between the snowball and the ground, and then the snowball rolls without slipping throughout the whole motion. So no slipping. Okay, another assumption, no slipping. And they condition they gave it a name, no slipping condition, NSC. So The third condition is that in order to accomplish the previous condition, so no slipping condition, the frictional static force that produces the rotation of the snowball has to hold the condition that it is less than or equal to friction coefficient times the normal force. Yeah, I mean this is just it's not a condition, it's just a given. This is known, right? This is known. This is always the case. There's no way that anywhere in the world, nowhere in the universe, it will not be the case, right? That the maximum static friction force will be mu s times the normal force. This is always the case, right? It's not a condition. It's just the way it is. Okay, so all right, so that will be and then they talk about we assume that s mu s is independent on the load. A Montan's law. I'm not sure what that is. Yeah, I'm not sure what a Montan's law. I'll probably look that up later. I mean, we can Google it. Let's see. A Montan's law. What's a Montan's law? Let's check it out. Um, so from what I get, okay. Let's see. Amonton's law was discovered in the late 1600s by the French physicist named Guillaume Amonton. According to Amonton's law, if the volume of a gas is held constant, increasing the temperature of the gas increases its pressure. As the pressure of a gas increases, its pressure increases as well. Um, okay, so I mean, I'm not sure what they're trying to tell us here, right? Because this is a gas law. Apparently, this is a gas law. So, what's the gas here? What's the gas that is involved in this problem? I mean, I guess you could argue that as the snowball is rolling down the hill, right? The the so the particles of water that are iced, right, that are in solid state, will of course will gain some energy because of that friction, right? Friction is essentially so there's a reason why there's friction, right? And that friction, well, theoretically should should take some mass. It should take some, excuse me, it should take some energy from that initial potential energy, right? So that initial potential energy, right? So initially all we got is gravitational potential energy, the mass of the snowball times the gravitation, acceleration times the initial height. And of course, the mass is not going to be constant all over, so it's going to be changing. Of course, it's gonna. So as you see, it's kind of interesting because over here we see that if the mass goes up and the height goes down, right? We want to know what's going to be the function of the mass. So like if we find the function of mass as a function of the height, and we are able to see what's happening as mass increases and then the height decreases, well, we'll see how the potential energy will behave. It seems like the potential energy, right? Just from looking at what's going to happen, will stay somewhat constant, or might increase or might decrease by some factor, but not sure what it is. Well, Amonton's law. Okay, so let's see the context because they're saying we assume that mu s is independent on the load. That okay, what is the load? So it's talking about the normal force, I guess. This same applies for not very large loads. Apparently, a mountain's load, okay, has to do with friction. So maybe I should probably look at the relationship between a mountain's law and friction. Well, let's see. Dating back to 1699, a mountain's law of friction. Okay, there is a law of friction for him. Assert that there exists a proportionality between friction force and the applied load, and that the friction force is independent of apparent contact area. Oh, right. So, like they're saying, of course, it doesn't matter how much, how much portion of that sphere on the bottom part is going to touch the ground, right? It's independent. That's always the case. That's always the case. It's completely independent. The friction does not depend on how much area you're basically applying that friction on, right? So it doesn't matter how much it is. You're always going to have the same friction coefficient. It's not going to change. Yeah, that makes sense. Okay, so I just gotta had to look that up, but no problem. So okay, then the fourth assumption is that of course the drag force caused by the wind is assumed to be in the form F equals negative rho A, so basically coefficient of air density and multiplied by the coefficient of air drag and multiplied by the area, right? The cross-sectional area of that ball, which is basically pi r squared of that sphere, multiplied by the square of the velocity divided by 2. That's going to be the force of drag. They assume that the drag coefficient is constant. Okay, I guess that's okay. To assume that it's constant. I honestly haven't really gotten into any of those problems where you have changing drag coefficients. I mean, I guess it's when you have gusty winds and like wind flows are constantly changing. Like that would be a more realistic kind of problem, but I guess it would be reasonable to just make it constant, right? It will be absolutely insane if it was not constant. Okay, so assuming you have like if you set up the experiment, right, and then you have a fan, you have a fan, or maybe some sort of like a a stream of air, constantly flowing against that incline. I guess that would be a good setup for an experiment, right? Um, then let's see. So it has been established that the force of drag could be a linear or quadratic. Okay, yeah, according to Reynolds number. For Reynolds number greater than 1, which is in our case a quadratic dependence. Okay, so I guess I don't really know what Reynolds number is. Let's see what that is. I'm curious. Reynolds number. Apparently it has to do with air drag. So no clue what is this. Reynolds number. Reynolds number is defined to be equal to rho, the density of the fluid, so the density of air in this case, multiplied by mu, or u, I think, flow speed, multiplied by L, characteristic linear dimension, divided by mu, the dynamic viscosity of the fluid. Okay, so, all right, I see. So this is apparently used to find the drag force. Okay, so I get it. All right, let's move on. Now the fifth assumption is this one over here, that the mass of the snowball increases, but finally reaches an asymptotic value. So it stops increasing afterwards. Furthermore, a specific function of the mass or volume in terms of time must be supposed. In our case, we assume the following functional form. M of t equals m0 plus k0 times 1 minus e to the power negative b of beta of t, where m0 is the initial mass of the snowball, and clearly the final mass is m of 0 plus k0, because as t approaches infinity, it's equal to m0 plus k0. So, yeah, I mean, I guess it's pretty good, asymptotical behavior at the end. They're assuming that it's going to stop increasing its mass, and I mean, I guess it makes sense, right? Like intuitively, you would say that the mass will start to like decrease as it starts increasing. Like when it has, I guess, the critical mass. There's going to be a critical mass where it just can't get anymore because of the rotational acceleration, right? The angular acceleration is going to essentially actually, like, you could think of that acceleration to be constantly increasing And if it increases by such a large value, well, what's going to happen is that little chunks of that snow, right, that the snowball has accumulated will start to leave the snowball in a tangential manner. So it will start just like shooting snow, all over the place in a tangential manner. And if that's the case, then it's going to lose, right? It's going to lose mass and as it gains mass, right? Because it's rolling down. So I guess, it's a reasonable approximation. I'm not sure why the choice, right, for 1 minus e to the negative b of t. I mean, sure, yeah, it's a decreasing exponential. It's seen a lot of times. It's very common to see it. Particularly for first degree differential equations. It's very well known. In electricity, it is very well known, right? So they're assuming this it has some sort of electrical connection, right? Has a connection to electricity. Okay, so then for assumption 6, a Hill profile must be chosen in order to make the simulation. Like in any other similar problems, it has an important effect on exit speed. Specifically, we've chosen an inclined plane and an exponential trajectory. Okay, so the trajectory is different. It's not going to be flat. And here are the equations of motion. Okay, so this is part 2.2. So let's see how much time we've gone over this. So it's only 21 minutes. Okay, I'll probably go over this for like a couple more minutes and then just do the rest later. So okay, here is a free body diagram. So we have force of gravity is in red. We have normal force in green. And over here is drag and the friction is over here. Okay, this is an angle of theta, and the angle between the normal. What's the normal to what? Oh, this is the normal force, but then they extend this a little bit, okay, and they call this angle phi. So it's the angle between basically the normal force and basically the complement, the supplement of theta. Okay, so the supplement of theta. All right. So, and they're assuming that the coordinate axis, the coordinate system is like this. So x is going to be in the direction of the incline and y in the direction of the normal. Okay. So, all right. Okay, so to simplify the problem, we start assuming the snowball rolling down the hill on a wedge whose angle is theta, and in the time t, the snowball has mass m, and in the time t plus dt, its mass is m plus dm. Okay, so I guess they're saying that at a particular time it's going to increase, right, its mass by a very infinitesimal amount. So let us consider a system consisting of the original snowball of mass m plus the little piece of snow with mass dm. At the time t, the momentum of such system is p of t equals mv, since the little piece of snow is still in the ground. And at rest, at the time t plus dt, the ball has absorbed the piece of snow completely, so the momentum is given by p of t plus dt. So like right after it has picked up that piece of snow, assuming that it's going to keep its spherical shape, it's going to be time t plus dt, and the mass is going to be m plus dm. And, this is basically multiplied by the velocity v plus dv. Okay, I'm not sure about that. Like, I've never seen that before, right? Like that kind of thinking in calculus. I mean, I guess it makes sense, right? You're just going to add an infinitesimal. You're thinking in infinitesimal terms, right? You're adding an infinitesimal size of of snow, right? Infinitesimal amount of mass for a particular time, right? An infinitesimal period of time. And the v plus dv, I'm not sure about that. I guess it makes sense that the speed is not constant and that you're gonna pick up speed. However, I'm not sure if that's valid. Yeah, I'm not sure. And then the momentum changes dp. Okay, they take a derivative. Okay, so take a derivative and they just do the basically product rule over here, and they assume that velocity is always changing, which makes sense, right? The velocity is going to be changing. It's going to be increasing. It's going to be increasing, and ideally, if you have no slipping, well, the energies will just be the mass, the initial mass. So, like the initial energy, is going to be mgh, right? That's going to be basically the total energy, or is it going to be the total energy, right? Because what's going to happen is energy is also depending on the mass, and the mass is increasing. So like if this is the initial energy, what's going to be the energy at any given point, right? So like what's going to be the energy if you like let's say when we give it a bottom. So like if it starts on the top, and then let's say we say, okay, what's going to be the energy at the bottom when there's no more decrease, right? No more decrease in the height, right? So from height h0 to a height of 0. So there's no more potential energy. However, there's going to be kinetic energy. So one half whatever that mass at that point in time is, m of t at t equals a t final, I guess, let's call it, or mass final. Yeah, I should probably just change it. So there's going to be a half m final v final squared plus one half um, I, right? It's going to be a one half I. Now I is going to stay constant since it's always spherical. The moment of inertia of a sphere is just 2/5 mr squared, and that can be easily calculated by taking the volume integral. So by taking the volume integral of rho x y z dv to find the moment of inertia multiplied by the square of the radius, and this will be the moment of inertia for any rho, uh, be it constant or no, right? If it's not a constant distribution of mass, and maybe if it's changing, then you can use this one, or you can just use the simplified version. The moment of inertia is the integral of dm, so r squared dm. Yeah, and then so then you get 2/5 mr squared. It's always going to be the same, 2/5 mr squared, right? So it's going to be the same formula. However, it's not constant because you see the mass is changing. So, di is going to be 2/5 r squared dm, right? Or actually, that's not the only thing that's changing. Did you notice? The radius is also changing. So if you think about the moment of inertia, well, it's just 2/5 dm r squared plus 2/5 times 2r dr times mass, and that will be the moment of inertia at any, basically the differential of the moment of inertia. The rate of change of the moment of inertia with respect to the m or dr is this one, in differential form, and so it's not constant, right? It's not constant at any given time, and if you want to integrate, I guess, with respect to how much mass it takes to get there. So let's see, and then we have half I omega square will be the rotational, the rotational energy, rotational kinetic energy. So it's not very trivial, right? And then they say that so where we have neglected the differential of the second order. So okay, apparently there would have been a second order differential equation. I guess that's because if you essentially take a derivative of that, so like the derivative, what if you take a derivative with respect to time? Okay, you take a derivative with respect to time of the momentum at t plus dt. Okay, so in that case you have to do a chain rule, and right, chain rule in here. So there will be pretty much d squared dt. Okay, d squared dt divided by dt squared, correct? So that'll be I guess the second derivative, the derivative of that. Well, no, that really doesn't. That actually cancels. So that would just be the derivative divided by the derivative of t. Um, and so this is basically, so this is 1, but this one will be, so this one will be twice. So it's going to be the second derivative, correct? That will be the second derivative. So d over ddt of dt. Yeah. So d over dt. So it's going to be d dt over dt, right? So then the d dt is d squared dt over dt. Yeah. And that's going to be multiplied by essentially p. So basically p of t plus dt and dt, dp dt. Yeah. So it's not easy. And then they said that they neglected the differential of second order. Why? Why would you neglect it? Is it too complex? F equals dp dt equals mdv dt plus vdm dt. Okay, I guess they used uh, the form where when you don't consider the addition of the infinitesimal time dt or the infinitesimal mass or the velocity, where v corresponds to the velocity of the center of mass respect to the ground. Okay. Okay. So all right. So then yeah, of course, the moment of inertia will be with respect to an axis that passes through the center of mass, perpendicular to the sheet. So I guess perpendicular to basically the incline, I guess, in figure 1. So let's say figure 1. Oh, okay, perpendicular to the sheet. So basically like going across but not touching the incline. Yeah, and crossing the center of mass. So the moment of inertia is IC omega c. Um, okay, so IC is the moment of inertia of snowball measured from an axis passing through the center of mass, and omega c refers to the angular velocity. That's the angular momentum. So the derivative of the angular momentum is the torque. So you get the torque since the derivative of angular velocity is angular acceleration. And they say that we should remember that this equation is valid even if the center of mass is not an inertial frame, which is clearly our case. To calculate the derivative of the angular momentum, they make an analogous procedure. Okay. So they say that IC d omega dt plus omega dic dt equals tau. Okay. So they're saying that the moment is not constant. So that the moment of inertia is changing. And I guess, yeah, that makes sense. It's because the mass is changing. Now, so here's basically the sum of the forces. Sum of the forces is the weight plus normal force plus the force of friction plus the force of the air drag, right? Yeah. So, okay. So, yeah, and then the paper goes on to solve for these equations. Here they solve for essentially these differential equations. They end up with these differential equations. So because the radius is not constant, so NSC, what was NSC again? NSC was, so the condition for no slipping. Yeah, no condition slipping. So this is no slipping condition. So they say that for the no slipping condition, you have to be careful because the radius is not constant. So the correct no slipping condition in this case is the relation of ds equals r d phi. Okay, so then v equals ds dt equals r d phi dt. All right, equals r omega. So So they're differentiating with respect to time because as time goes by, the radius will start increasing. It's going to be changing with respect to time. Um, and then they end up with this second degree differential equation. Okay, so it's R F equals I, and then all of this over here. So okay, so yeah. So then they try to take the derivative of the moment of inertia, just like I tried on the top, and they get this. They get 2/5, right? R squared m dt plus 2m r dr dt. Okay, and yeah. So then the mass is basically 4/3 by rho r cubed. Of course, the radius is changing, so take a derivative of that, and it's dm dt equals 4 pi rho r squared dr dt. Okay, so they say that and notice that you can start with the traditional no slipping condition with v equals omega r. Nevertheless, the other traditional no slipping condition, alpha is r omega, is not valid anymore. And that's because the radius is changing. So the radius is changing, so you should not be able to use any of those, right? Okay, so and then over here, they just add up all the forces. Okay, so this is the sum of the forces, and then you get a second degree differential equation. And I think this is pretty much well, everything's in terms of time, right? So it's just it's not a linear differential equation, right? It's not linear. So then over here, they talk about, so then in this part, they're going to talk about the different trajectories to consider for this problem. And the differential equations are definitely not easy to solve. And they say that there's no analytical solution. So that there's no analytical solution. And they move on to talk about basically the trajectory. I guess I'll be talking about this some other time, to break it down, I guess, a little more. But I guess that's it for now. So if you like the video, hit the like button and subscribe if you haven't. And make sure to check out my Patreon and subscribe for as little as $1. So thanks for watching, and I'll see you next time.